In this video, we're going to revisit implicit differentiation. So what we want to recall is our two variable, x and y, both functions of t, our two variable chain rule. And so this leads to a formula which can take some of the algebra out of implicit differentiation. So we are going to assume two things. We're going to assume we have this function xy and it's differentiable. And then also what we're going to assume is that the equation f of xy being equal to 0, that this can define y implicitly as a differentiable function of x. So that's a differentiable function of x. So say we have y is some h of x. So what we can say, w being that function of two variables, if that's equal to 0, then the derivative dw dx must also equal 0. Further, if we take what we're doing, we're going to say, and let x equal t. So let's think about this as our dependency diagram, right? So it's a beautiful diamond I'm making here. So here's w, my dependent variable. W is a function of fxy. So we've got some x and some y being h of x. X and y equals h of x. These are my two intermediate values. And we said we were going to let x equal t. So I'm going to put an x here where we might normally have a t. So traveling down my dependency diagram here, this is the partial of f with respect to x. And then dx dx would equal 1. Similarly, we've got the partial of f with respect to y, f sub y, and here we would have y prime, or the derivative of y with respect to x. So this kind of allows me, thinking about this dependency diagram in this way, what we're going to do is to redefine this chain rule. So dw, the derivative of w with respect to that independent variable x. So dw dx, so that's going to equal this product, f sub x times 1, plus this product, f sub y times dy dx. F sub x times 1 plus f sub y times dy dx. All right, now what we set up above was because if the function was equal to 0, then the derivative would equal 0. So I'm going to plug in 0 for dw dx. F sub x equals, that would be a plus f sub y dy dx. So we've kind of redefined this in a way, now that we know the chain rule and we kind of understand the dependency diagrams, we created some conditions that we were able to develop this equation. This is my derivative of y with respect to x. So can I isolate that? And the answer is sure. I would have negative f sub x equals f sub y dy dx, or rather dy dx is negative partial of that function with respect to x divided by partial of the function with respect to y. So this is kind of a new way to think about implicit differentiation. It's a shortcut rule. So writing this a little more formally, suppose f is a function of x and y. If that equation, that function is equal to 0, if that defines y as a differentiable function of x, then as long as that partial of y, or the partial of the function with respect to y, as long as that denominator is not 0, then we can define the implicit derivative in this manner. All right, so let's look at an example. So for this example, we are given an implicitly defined function, and it's equal to 0, which was one of the conditions. And not always will your implicitly defined function that's given be equal to 0, but you can always move all of the terms to one side, and then it would be equal to 0. So as long as you have this equal to 0, then we can use this shortcut formula. So essentially, we're going to find the partial of the function with respect to x, divide it by the partial of the function with respect to y, and then negate it. And really, you know, I get messy. My minus signs always begin to look like they are in the numerator, but essentially it's in the denominator. That should look like a sub. So that looks a little better. So in order to find this derivative implicitly, we're just going to find each partial and then find that quotient and negate it. So treating y as a constant, y squared would be a constant. I have 0 minus x squared. That derivative is 2x. And then the derivative of negative sign of some constant y times x. So finding that derivative, y is like a coefficient in here, so we'd use the chain rule. The derivative of sine is cosine, so that negative is there. I've got cosine of xy, maybe I should have parentheses up there. So cosine of xy times the derivative of the inside, which is xy or yx, y being that coefficient, we have y. So the partial of the function with respect to x is negative 2x minus y times the cosine of xy. So that's what I'm going to put in my numerator. And the partial of the function with respect to y. So differentiating that, I've got 2y, x squared would go to 0, and I will get negative. I'm going to have the derivative of sine is cosine xy. So now we take the derivative of the inside, treating x as a constant. It would give me times x. So I'll put that in the front, and I have x cosine xy. So my implicit derivative, or my derivative dy dx, found using this new implicit formula, using the two partial derivatives, is negative 2x minus y cosine xy over, looks messy, 2y minus x cosine of xy. And so that negative in the numerator turns that into dy dx is 2x plus y cosine of xy over 2x minus x cosine of xy. So this is really a much shorter calculation than if we had done a single variable calculation to implicitly differentiate this function. All right, so I hope that helps. It's a kind of a new shortcut we can use. So yay for shortcut rules. Have fun, be safe, you're on your own. Just kidding. Email me if you have any questions.